Okay, I think this is working. If not, I'll find a way. Share my screen. All right, so this is question 7 through 9 on the quiz. This is low-key a blind run through, but it's okay. I read this question and then I low-key had to do a little bit of Googling, but I think what makes it more clear is the fact that this wire we're treating as situated, like it's just like it's sitting there, it's not moving. Whereas this rectangle is what we would kind of want to figure out, like what's going on with it. So this wire is going to produce a magnetic field, which looks like this. It's going to be rotating around like this. If we take our right hand rule and we say current's pointing in this way, so field has to always be going that way. So then we can use Q, V cross B, and we can use the linear form and we can say IL cross B, but you don't even really need to, like, the important part is this cross. And so a cross will be like a sign product, right? So we have our current is moving. So if we, right, because, okay, sorry, let me like make a real sentence. The ones which are directly pointing towards and like against it, this cross is going to be 0, right? The sign of theta is going to go towards 0. And so that's fine. That's great. But that means that the y here and the y here are going to be affected. So we can say IL cross B. If I have current moving like this in this direction, and it's a magnetic field which is coming like this, so at this point, it's, or like at that plane, it's going to be pointing out of the field. If I have a bow and it's pointing towards me, out of the field is going to be a dot. So you're going to have out of the field lines here and into the field lines, or sorry, into the page lines here. I was always told to put circles around them. I don't really know. I'm not a notation. Actually, that's so untrue. I'm such a notation fanatic, but like not about this thing. Like I couldn't gaff. So if we have our velocity going this way, our force going out, then we're going to have a force pointing down on this. And this makes sense because it's not doing any work on the system. So this is going to be pulling down. And then this one is also going to be pulling, this one's going to be pulling up. Just in like, if we have our velocity going this way and our field going this way, then our finger is going to be going up here. So it's going to be pointing up. Wow, that looked really insane. If we have our velocity going this way, our field pointing out of the page, then our force is going to be up. You guys, I'm assuming you guys did the 3-hand rule where it's like vector 1, vector 2, and there's your cross product. If not, now you know. I've not been keeping up to date on the lectures, and that's on me. So we know that because this is closer, it's going to experience, the magnetic field strength is going to be greater. So the force down is going to be greater than the force up. So the net force is going to be downwards. And we know that since the force isn't coming in or out of the page, there's no torque. All right, let's see. The magnetic force should be pointing downward, and the net torque should be 0. So the answer is going to be E. All right, let's look at problem 8. In the figure, what am I looking at? Oh my God. A straight wire carries a steady current I perpendicular to, okay, so this is a wire, and it's carrying current perpendicular to the plane of the page. So it's pointing out of the page. I've never heard perpendicular to the plane of the page. A bar is in contact with a pair of circular rails. Cool. That's actually really cool. They're in rotation about a rotate wire. Their direction is the induced current through the resistor R is this. Okay. So we have this area and oh my god, what's the equation? Your change in magnetic flux over time is equal to voltage, your EMF, which is equal to voltage. You have to say EMF. You can't say voltage, but EMF is in volts, so I just call it voltage. Which is equal to your magnetic field times your area, which is usually denoted as magnetic field dA. Okay, so this is our equations. Let's see what we can do. The direction. Oh, I'm way overcomplicating this. So cool. We know that if the magnetic field is pointing out like this, there's a magnetic field pointing like this. Which means if I were to imagine it as a net, if I imagine this as a net, the amount of magnetic field that I'm capturing in that net is 0 because it's not placed like this. If it were placed like this, the magnetic field lines, think of this as magnetic field lines, right? Like there's really strong field lines and then they get weaker, but they're all pointed in this direction, you know, like to the page like an onion. And so it won't capture any field lines, like any field line that goes like it'll. Does that making sense? Like it doesn't. Here, let me. This is how it was explained to me of like magnetic fluxes. Imagine that these are magnetic field lines, and it's all of the field lines that go through an area. And so in this scenario, you have circular field lines like this, and your square per se is also circular. So it can't capture any, right? Like it's skinny in the wrong way. Versus if it were to be laying flat like this. Wow, he's so good at drawing 3D. They all say in unison. And the magnetic field lines are coming out. It'll go through that page. Wow, perspective diagramming. Almost there. Keep moving for 1 minute and make your progress towards your stand goal. All right. So this one, there is no induced current through the resistor because your BDA, like this dot product, is 0 because your cosine between these two is 90 degrees. Or as we say in the engineering world, pi halves. It's pi halves, guys. All right. So that's fine. All right, problem 9. We're chugging through these. I hope that this isn't taking too long. In the figure below, 2 parallel wires carry a current of magnitude I in opposing directions. Oh, it's one of these problems. Love it. Rectangular loop is midway between the wires. Love that. The current I is decreasing with time. Okay, so we know that the field lines are going into the page here, and they're going into the page here. So we know that this area has a decreasing field strength and the same area. So that means it's going to be negative change in flux because this value is going down over time. Down over time. So our change in flux over change in time is some like negative value. Let's just say like negative alpha. Oh no, don't click me out of the call. I know I'm the only one. Stay in call. All right, so we have some negative value for our EMF. So that means, I think this is actually the wrong way to go about it. I'm so sorry. It works if you want to find a number, but I think what's important to note is that you have a decreasing like flux going through there, and nature abhors changes in magnetic flux. That is like, I cannot stress that enough. Nature abhors changes in magnetic flux. So it's going to have an induced current. I don't know if I drew it the right way. We're going to find out. Where it's going to create a magnetic flux inwards. And so, wow, physics, we really do look crazy. We need a counterclockwise. Sorry, we need a clockwise current, because a clockwise current will make a current like that, or like a magnetic field like that. So it will counteract the change in magnetic flux. So it will go from B to A through the resistor. It'll go from A to B through this wire, and from B to A through the resistor. The induced current through the resistor R is from B to A. So you would do that. I really like these problems. They're my favorite, and they make me feel really like competent at 3D modeling. But it's just the right hand rule in action, and just remembering, right? Like that's what I was doing there. I was saying, oh, nature abhors changes in magnetic flux. It's going to want to create a magnetic flux in that direction. So in order to create a magnetic flux in that direction, a moving proton, because these are all about protons. So a moving positive charge would need to go counterclockwise or go clockwise in order to make a like that into the page. And out of the page is what's happening out of here. Does that make sense? It's quite cool. It's cool. So that's one thing. Oh my god, like my brain is like fogging. Yeah, that's the thing. All of the equations describe positive charges as if positive charge is moving, because the guy that discovered it, it's a lot easier to see a proton than it is to see an electron. And so they acted as if the positive charges were moving. And then you do some micro physics, and then it's like, no, that doesn't make sense. And that's how they proved that the electron that's one of the ways that they proved the electron existed before being like, that's an electron, is that they proved that positive carrying charges are deeply infrequent. And when we're talking about current, we're more often than talking about moving electrons or photons. Anyways, that's my fun fact of the day. I hope this was helpful. That's just kind of how I approach these problems. Is I say, okay, is the current changing? Yes, no. If the current's changing, it's describing that this field is, like, you're essentially saying that it's becoming negative, and so you need to repositify it by making some sort of induced loop, which would go like this, in order to push magnetic field back in. Yeah, I hope that this made sense and was helpful. That like this will capture none of the field lines, this will capture some of the field lines, this will capture all of the field lines. And then this one is just this is fixed, this is not, and you're not really focusing on this, you're just focusing on this. And it's seeing that the ones which are not orthogonal, perpendicular to the wire, won't have any work done because the cross product, right? If I am moving upwards and my field line is like that. Oh, totally lied. Let's re-examine problem 7. I think I crossed that out too soon. That's on me. So we have our velocity going upwards, we have our field line pointing out, and we have this coming out. So this is there's a force coming to the right. Sure. We have this coming down. We have our field line coming out. We have this pointing to the left. Okay. How there would be a torque is if there was a force coming out or into the page, because then that thing would spin like that, which we've had problems like that where he might ask you a problem. I don't know if the final is cumulative, and if it is, I wouldn't be surprised if he's saying this is held by a string. There's a field lines that go like this, like your magnetic field is in this direction. What is the torque at that point, at that moment? Because it changes. Yeah, you did it. You earned another hour towards your stand goal. Love that. I don't know when I stood, but good luck. You got this. And let me know if you need anything else. Okay, how do I end this recording? I think I'll just hit the stop record. Yeah, okay. Take care.